Next, we're going to look at this problem. This is 15-61, 15-61. And we have a 15 kilogram block A, and it's sliding along the surface. I believe this is a misprint. It says M sub K is 0.3. I believe that should be mu of K is 0.3. Now, that would mean that the coefficient of kinetic friction is 0.3. The kinetic coefficient of friction is 0.3. Then the block has a velocity of 10 meters per second when it's 4 meters from block B. And block B is 10 kilograms. If the unstretched spring has a stiffness of 1,000 newtons per meter, determine the maximum compression of the spring due to the collision. Take the coefficient of restitution to be 0.6. So we have this block sliding to the left of block A along this surface. The surface is not smooth, but it has a coefficient of kinetic friction of 0.3. And then it's going to strike block B. And we have to determine the maximum compression of the spring. I think we did the first part from starting point until A reaches B. And we had that the normal force, the normal reaction here was going to be 15 times 9.81. 147.15 newtons was the normal reaction. And then our friction force was going to resist it. And again, our friction force is going to be our 0.3 times 147.15, which around 44.1 or maybe 0.2 newtons. And then we could just use work energy, T1 summation U1 to 2 is T2. And the original kinetic energy is 1/2. And our block mass was 15, 10 meters per second squared. And then the only work being done going when it goes from A to B is going to be our friction work. That's going to be negative our friction and times our distance, which was 4 meters. And the right-hand side, 1/2, 15 velocity final squared. And again, our friction force is going to be from up here. So it's going to be 1/2, 15, 10 squared minus our 44.2 times our 4 meters, 1/2 mv squared. And you put that on your calculator, you'll get that the velocity of block A is going to be 8.74 meters per second when it reaches B. So we're going to have that. So we need to find that's the first step for when it goes from where it starts to B. Then next, we're going to find the impact. So this is going to be like the moment when A impacts B. So they come together at this point. B is 10 kilograms. A is 15 kilograms. And so we're going to have to use conservation of momentum. So the velocity of A, and I guess we don't really need numbers for the mass, since they're not going to change. So I'll just call it mass of A. And then the velocity of A before impact, velocity of B before impact, velocity of A after impact, velocity of B after impact. This, once again, B was at rest, so that's going to be 0. So we have 15 times 8.74. We just found from the last page, plus 0, and then just put the mass of A, the mass of B, and then we can rearrange this. If you put all the constants on one side, and let's see how we want to rearrange this. I'll make this 15 VA2 equals, and we multiply this together, get like 131.16, and bring this over the other side, minus 10 VB2. Divide by 15, we get VA2 is 8.744 minus 0.67 VB2. And we have 2 unknowns and 1 equation, so we need another equation. Call this one equation 1. And then use our coefficient of restitution. And remember, it's going to be VA2, VA1, VB1. Use that equation there. And we're given that E is 0.6. VB2 minus VA2 divided by 8.74 minus 0. And then if we solve for VA2, we get VB2 minus 5.244. And we can call this equation 2. And notice in both equation 1 and equation 2, we have VA2 equal to something. So we can just set those 2 equations equal to each other, huh? Set equation 1 equal to equation 2. And so when you do that, 8.744 minus 0.67 VB2 equal VB2 minus 5.244. And then if we solve for VB2, we get 8.376 meters per second. Velocity of B just after impact. Now we probably won't need it, but just to be sure that everything seems reasonable, we should see what's happening with A. So we can just use one of these equations. Let's say if we used, so we have equation, we can probably just use equation 2. And find the velocity of A after impact, and that's going to be 8.376 minus 5.244. So this is 3.132 meters per second. So we just mainly want to be sure that B is moving faster than A. And if it wasn't, then there would be something wrong, because, B is going to the left. So A either has to be moving at the same speed, slower, or it could move to the right. But what happened, we ended up being, so that checks out. But main thing that we needed, though, was to have that velocity of B. So now we have B moving to the left. So it's going to start to compress the spring. So this time go from impact until B stops. So just get an idea what we have. We have a picture like this. B is moving at 8.376 meters per second. And so once again, since we have a spring, we can use like work energy again. T1 summation U1 to 2 is T2. And at the beginning, it's moving at 1/2 mv squared. And then the only, we can assume, I guess, that there's no friction. I think when I did this, I think in order to match the answer in the back, I think I had to assume, let me just check, I had to assume no friction. Let's see when. Yeah, so assume no friction. And so the only force is going to be the spring force. And so it's going to be minus 1/2 K, which is going to be our, what was it, 10,000? Yeah, 1,000 times our delta S squared. So I'll just put like S squared. So remember, this is just our spring constant, S squared. That's the only force acting on it. And then we want to find the point of maximum compression. So that's going to be when the block stops momentarily. So the right-hand side is going to be 0. So if you put all this in your calculator, this is 350.8 minus 500, S squared is 0. And S is going to be 0.837 meters. That'll be the maximum compression.